Welcome to our crash course in how to work with matrices. We're going to talk about multiplying matrices, determinants of matrices, and linear independence of vectors. This is all stuff that's often covered in a linear algebra course. We're going to go through it pretty quickly. We're not going to really spend too much time talking about the theory or why it works. We're just going to say, here's how you do it. So that later on in this section, and especially later on in this chapter, when we require something from this, we can always refer back to this video, refer back to this section in our notes. All right. And that way we don't have to introduce a bunch of things in the middle. We can just kind of introduce it all now and refer back. So it's going to be a lot of definitions. It's going to be a lot of new things probably. Just strap yourselves in and know that you don't have to memorize it all today. We'll be using it and practicing it as things go on. I will also share a handout. I'm going to share a handout with a lot of these properties and definitions so that if you want to, you can write them down in your notes or you can use the handout. Anyway, so let's look at a matrix A. We're going to write matrices. I really don't like a lot of how this book does notation, but this book uses parentheses. A lot of times you'll also see brackets for matrices, but something that's really important is that there's going to be a capital letter. Okay. I actually don't know which capital this is. I think it's capital. But anyway, so we have a matrix right here. And let's say we have a vector. Again, we're using that vector notation. Maybe that's a vector of x's and y. Then essentially the way that we can multiply a matrix and a vector, which again is a, b, c, d, times a vector a, x, y. How do we multiply a matrix and a vector? We're going to do it with some sort of weird kind of thing. We multiply and add across, and we create a new vector. So this is going to be ax plus by, and then we're also going to have, multiply those two, cx plus dy. That's how we multiply matrices and vectors in short. And you can see why this is going to be very useful to us, right? Because we're looking at linear systems, and so we can write that as a matrix of constant coefficients and our dependent variables, which will depend on time. Okay, and this is just a really nice thing because a lot of properties about our linear systems will depend on this matrix right here. Okay, so in general, we can kind of make this more generic. We can go further with this. Let's say that we have another matrix, and let's make this matrix a bit bigger. This is A11. A12, and we're indexing all of these coefficients all the way up to m. And then we can go A21, right, all the way down to AN1. And again, what would be right here, A22, right, and this, it all dot, 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 A and M. So we can really also have an n by m matrix. Right, matrices can be as big as we want. The idea right here is that n represents the number of rows and m represents the number of columns. And that's really useful because we can only multiply certain matrices together. Specifically, we can only multiply matrices if the middle number matches in terms of its dimension. So here's what I mean by that. So we can multiply a 3 by 4 matrix by a 4 by 5 matrix. That's okay to do, right? These things right here match. This is okay. But what we cannot do, right? We could not multiply a 3 by 4 matrix by a 5 by 4 matrix. This would not make sense. All right, and the reason why is in how we did it, right? There has to be the same number in this row of items as there are in this column. So what does matrix multiplication look like if we have bigger matrices? Let's multiply another matrix. Let's see, let's do an example. What else could matrix multiplication look like? let's just count up to 9. A 3 by 3 matrix here. Right? This is 3 by 3. And let's multiply it with a bunch of variables. x1, x2, let's say y1, y2, and z1, z2. So we can multiply these two matrices together, right? Because what is this? It's an n by m. We count the number of rows, we count the number of columns. This says 3 rows and 2 columns. And again, we can see that these match, so we can multiply these together. How do we multiply matrices? You might not know, that's okay. And again, the result actually is always the other numbers. So the result here will be a 3 by 5. The middle numbers match, but they're actually not part of the result. So what is our result going to be here? We expect a 3 by 2 matrix. So if you do that, how do we multiply? Just like before, we do this and we add them all up together. So I need more room. I need more room. So this is 1x1 plus 2y1 plus 3z1. And then we do that for the next column as well. Right? We could do it row by row first and then do it in the next column. It's up to you. But these also get multiplied. The second one, oh my gosh, this is nonsense now. Right, and then we're going to also have 1x2 plus 2y2 plus 3z2. Luckily, we're really not going to do much matrix multiplication that has multiple columns in the result, but this is how it goes. And then again, 4x1, 5y1, 5z1, and we'll just go on, so on. And then making sure, and then these are really just going to be the exact same, just for the x2s. All right, and then finally, what do you think the last row is going to be? Pause the video. See if you can get the last row on your own. All right, it's going to be the exact same process. 7x1 plus 8y1 plus 9z1, and that will be all the same things over here, just with 2's. And you can see, right, that our result is a 3 by 2 matrix. 3 rows, 2 columns. And again, each entry is a little bit more complicated, but that's how we can deal with matrices. Now we'll become a bit, will come into play later. All right, what else are we going to need to know about matrices? We have a lot of definitions coming up, so strap yourselves in. We're going to talk about something called the determinant of a matrix. And specifically, let's talk about 2 by 2 matrices right now. The determinant of a 2 by 2 matrix, let's say that is the matrix A, which is A, B, C, D, is written as the determinant of A, and it's just A times D minus B times C. So it's just a number. The determinant of a matrix is a number, and this number is going to be important. It's important to a ton of linear algebra. We'll talk about why it's important in this class coming up. Again, just kind of getting some definitions in front of you that we can work back with later. So maybe that's definition number 1. And any square matrix actually has a determinant. We're only looking at 2 by 2 matrices here, but any square matrix will have a determinant. They just get more complicated to calculate. But we're mostly going to work with 2 by 2 systems. They also are called planar systems. Let's go through these definitions quick so we can be done with this video. Thank you for sticking with it. If determinant of A is equal to 0, so here's one use of the determinant, then A has a special name. We'll say if the determinant is 0, we have a very interesting situation. And we'll say that the matrix is singular. You may also hear the term degenerate. I frequent the internet, so I actually hear this word too often, used in other contexts. But anyway, This is basically what we have right here. And then otherwise, if the determinant is not equal to 0, it's known as non-degenerate. As far as I know, there is no definition for multiple, or the opposite of singular. All right, last couple things that we're going to talk about is some vector stuff. If we have two vectors, so we'll call them v1 and v2. If we have two vectors and two constants, k1, k2, these are both constants, real valued constants. Then if we multiply a constant times a vector and add it to the other constant times an other vector, that's known as a linear combination. Okay, so for example, we'll visualize this a lot more later on in this section. Let's say that I have two vectors, and maybe one vector looks like this, and maybe another vector looks like this. Then I could add them together, right, to get a third vector. This yellow vector is v1 plus v2. But really, I could do double the first and the second, and that would also work, right? Any multiple of v1 and v2, and we add them together, that's going to be a linear combination. And that's going to be really useful, specifically when talking about linear independence. Okay, so the last one is that v1 and v2 are linearly independent What does that mean? If they aren't multiples of each other. So if they're multiples of each other, then we have very silly linear combinations, right? If v1 is just double v2, we have very boring linear combinations. But if they go in slightly different directions, and that's another way of saying it, right? They're linearly independent. If they go in slightly different directions, but also not opposite directions, you could say whether they stay on the same line. Because again, if I gave this vector, this is not linearly independent from v1, right? It's just the opposite of v1. So these two are not linearly independent. But any other pair of two vectors here is linearly independent. And we can do some cool things with linearly independent. Specifically, if I have two linearly independent vectors, then any other vector can be written as a linear combination of them, which is pretty cool. So if I have two linearly independent vectors, I'll just make some up, right? Let's say this is v1, and we'll have v2 go some other direction. Then any vector you draw can be written as some linear combination of the first two. So essentially, right, to make v3, I have to scale v2 enough to get enough height so that, scale v1 enough to get enough height so that v2, I can really get myself far back to the left of here. All right. So maybe in this case, we'd have like 1.5 v1s to get up to here, and then we'd subtract a v2 to get to here, and then we could create our third vector. And you can create any vector with a linear combination of two other vectors, which is really powerful. And that'll be really useful when we try to introduce this linearity principle that we're going to talk about in chapter 3, about how can we find the general solution to a system of differential equations from just one or two solutions. And that'll be coming up pretty soon. So, okay, you survived. Again, lots of definitions here. Matrix multiplication takes a bit of getting used to. This is how you do it. I'm sure there's some cool explanations on ways to remember it or think about it. But that's pretty much the tools that you need for this section. And then again, we won't talk too much about why they work or what that stuff, but we're going to use them as useful tools for solving our systems. So there's your crash course in linear algebra for this section, and most painful section is out of the way. Good luck. Bye-bye.